Hello. All right, so here we are for I guess the very last video with any instructional content, or new material, I should say. And we have a couple of things to cover, and once those are covered, that'll be it for today's lecture. However long that might take, I rather doubt it will take the full 50 minutes. For next week, what I have decided, and we'll put in an email later, is that, as I think I said previously, I'm making some review notes. They are not exhaustive. This is not a guarantee that if you know everything in these notes, then you will get 100% on the final or anything like that. Just meant as a study guide. But I'm putting together a set of notes, which I hope to have at least mostly together by Monday or Tuesday of next week, and sort of entirely together by, so I'll release what I have when I have it, kind of thing. And I will release one or more videos, not necessarily on the same sort of rhythm as the ones that we've had so far. Basically, whenever I get time to do the review videos, then I will post them and I will send an email to let you know. But I will try and go over the notes that I post on Blackboard, and try to sort of hit the high points and stress this or that, remind you of some things. As far as asking questions goes, if you have questions, I'm certainly open to setting up a WebEx meeting with you, okay, on a sort of individual basis. I think it works better just having some kind of general meeting where people click in and out. I think it's going to be just a mess. What I would ask is, if you would like to ask some questions like that over WebEx, I do think it works pretty well. I mean, you can sort of hold up what you're asking, and I'm able to hold up, whatever solution I'm working on, or I could do it down here and work on the chalkboard. But what I would ask is that you do try to collect your thoughts before we have a scheduled WebEx meeting. That is, get to a point in your studying where you've got a list of questions, a list of things that you're confused about, a list of questions, specific examples that you want to work on. That way, then when I make time for you, it will be relatively efficient so that I can make time for other people as well, because it's going to require individual meetings for each person that wants to ask questions. So I will, schedule those to the best of my ability whenever you guys are available. Another thing, I received a number of requests, sort of anonymously through Piazza or directly, for wanting your midterm grade. I mean, there were one or two cases where it was somehow understandable for unique reasons that you didn't have it, but in general, really? Now? You don't have your own midterm grade? But anyway, if you really need that, I am not allowed to email it per FERPA regulations. However, if you email me directly, not through Piazza or some anonymous thing, but just email me directly and say, look, here's why I don't have my midterm grade at hand. Can I get it? Then, that involves me then making a PDF file with your grade on it and then sharing it with you on FileLocker. But if it is that desperate a situation, then you can email me directly about it. Okay? All right. I think that's all the organizational stuff I wanted to talk about. All right. So where were we last time? We had there's the end of the proof right there. So we had just finished proving that if you have a function f, and if it is differentiable at a given point, then the function f also has to be continuous at that point. So differentiability is a stronger property than continuity. And then I kind of wave my hands, and I do in the notes as well, saying, well, there are these basic rules for combining functions and taking the derivative, which you should all know well, like taking the derivative of a sum, of a difference, of a scalar multiple, of a product, or a quotient, okay? And in each of those cases, I mean, things get a little messier than they do when you're just working out the basic limit laws. But nevertheless, an application of existing limit laws kind of does the trick and follows more or less the same lines as the limit laws for sequences and subsequently for functions, okay? An exception to this, in terms of complicatedness, is the chain rule. So what I wanted to talk about today was the chain rule and how the proof of the chain rule can be carried out using something called Carathodory's theorem, which almost isn't a theorem at all. I mean, it really, when you look at it, seems to just be kind of restating the obvious or just renaming some obvious bits. But it turns out that in renaming sort of various pieces of the definition of the derivative and recasting it, you come up with a formulation that just happens to lend itself very naturally to proving the chain rule. Okay, so that's what we're going to do. And when we're done with that, we're done for today. Okay, so let's see. Caratheodory's theorem. I will not ask you how to spell it on the test. So what does it say? So let f be a function on some set I, where I is an interval of some kind, and C belongs to I. Then, so this theorem is a characterization of when the function f is differentiable at C. Then f prime at C exists if and only if there exists a function, we'll call it phi, from I into the real numbers, such that phi is continuous at C, phi of C is actually equal to f prime at C, and we have the following algebraic equality. If you look at f of x minus f of c, it's equal to phi of x multiplied by x minus c, where x here belongs to I. Okay, so what I mean about kind of like rewriting or just renaming bits of the definition of the derivative is that, if you look at this expression here, f of x minus f of c is equal to phi of x times x minus c, then if x were not equal to I, then I would be able to divide both sides of this expression by x minus c, right? And then on this side here, I'd have f of x minus f of c divided by x minus c, which is exactly the thing that you take the limit of to get the derivative, right? And on the other side, I would just have this function phi of x, right? Which there's nothing special about it other than it's equal to that quotient, f of x minus f of c over x minus c. What is special is that we have insisted that that phi be continuous at c, so that in particular, when you rearrange things and put the x minus c over here, what that's really saying is that the limit as x approaches c of f of x minus f of c divided by x minus c, that exists and is equal to phi of c. Well, it's also equal to the derivative of f of c when it exists, and hence you get this equality here. Okay? So it's almost like a kind of mathematical word salad. I mean, you're just kind of moving things around. But it turns out that casting things in this way, casting the differentiability of the function f as the continuity of this function phi of x at c, makes for a much, much simpler calculation when you're looking at the chain rule, as we will see. Okay, so let's first prove Carathodory's theorem. All right, so proof is the forward direction. Let's start by saying suppose f prime at c exists, which is another way of saying that f is differentiable at c, right? Well, if that's the case, then we want to produce this function phi of x with the properties specified in Carathodory's theorem. Incidentally, if I do wind up getting the coronavirus, I'm going to tell you exactly what it's going to be due to. This. Pushing, you're supposed to keep your hands away from your face, but these stupid glasses, which I like, new glasses, because the new glasses place is shut down for the coronavirus, I couldn't get them adjusted, so they kind of slide down, and so I push them up all the time, so that's going to do me in. That's going to be that, or teaching 500 students calculus in the fall. That could be it too. Anyway. Alright, so let's define phi of x. So let's let phi of x be equal to f of x minus f of c all over x minus c when x is not equal to c, right? Because we want phi of x to satisfy this algebraic equation, right? So I'm just going to make it equal to what it has to be equal to when x is not equal to c. And then I'm going to say, well, call it f prime at c when x is equal to c. Okay? And because we know that f prime at c exists, that means that the limit of this guy up here, as x approaches c, is precisely this number right here, which is another way of saying that this function phi of x is continuous at c. Okay? Ooh, I would also point out that equation involving phi of x, x minus c, and f of x minus c always holds when x is equal to c because both sides are automatically 0. You don't have to worry about that equation holding when x is equal to c. That always works. It's when x is not equal to c that you have something to show. Okay, so this is all you do. If f prime at c exists, here's the definition of phi of x. There it is. And like I said, it's just kind of like renaming and moving things around. Okay, now for the other direction, now suppose that phi is continuous at c, and that f of x minus f of c is equal to phi of x times x minus c. Okay, again, it's just kind of a almost trivial rearrangement of what you've got right there. Well, I'm going to say then that phi of c, that's the limit as x approaches c of phi of x. That's because I've supposed that phi is continuous at c, right? So that's the definition of continuity. On the other hand, I know what phi is equal to in terms of f of x. It's precisely the limit as x approaches c of f of x minus f of c all over x minus c. And so what this string of equalities is saying is that the limit that you want to exist in order for f to be differentiable does indeed exist. There it is, right? So whatever that number is the derivative of your function at c, okay? This is equal to f prime at c by definition, and that's what you wanted, that the value of this continuous function at c is in fact just the derivative of the function at c. So that's Carathodory's theorem. All right. Now we would like to use this to prove the chain rule. Oh, I did get an email. I'm supposed to remind you to fill out the instructor evaluation form. I guess you get a link or something like that, and it's my understanding that somehow they dramatically altered the list of questions for this semester because, well, you know, stuff happened. So I can't remember exactly what the email said, but it said something like, now there are only 3 questions. Like, I can't imagine exactly what those 3 questions are, but probably just like, you know, so did everything crash and burn, or did it say semi-stable? You know, like, I think they're pretty broad questions. But anyway, maybe there's a free form part where you can light me up. Anyhow, it was my duty to inform you that that's available now. Okay, chain rule. So let's let I, for convenience, let I and j be intervals. Let's let f be a function from j to the reals, g a function from I to the reals, and we will suppose that the image of f, every possible value that f can take, belongs to I, right? And the reason for supposing this is so that we can compose these 2 functions. We can form the composition g composed with f, okay? Then, if f is differentiable, so this is my little shorthand for differentiable. If f is differentiable at c in j and g is differentiable at f of c, which now belongs instead to I, then the composition g composed with f is differentiable at C, because remember the composition has for a domain the domain of the function f, right, which is j. Okay, so that's where we take our point here. Okay, so then the composition G composed with f is differentiable at C, and we have the familiar rule that, let's see, G composed with f prime at C is equal to G prime at f of C times f prime at C. Okay? All right. So I claim we're going to be able to prove this most easily using Carathodory's theorem. Let's see why. Most of the effort in this proof is expended just writing down the expression for Carathodory's theorem for each of f and g. The rest just kind of falls into place. Okay, so proof. First, use Caratheodory. Okay, so I'm going to use it on each of f and g. So I'm going to say f prime at C exists. So there exists a phi, a function phi, continuous at C such that this little algebraic expression holds. F of x minus f of c is equal to phi of x times x minus c. Yikes. All right. And then we'll also note that G prime, the assumption is that G prime does not exist at C, might not even make sense at C. G prime is taken to exist at f of C. Right, so G prime exists at this point f of C in the domain of G. So this exists. So there exists. So similar to the situation with f, we want a continuous function. We'll give it a different name. We'll call this one psi. And it will go from the domain of G to R. And it will be continuous at this fixed point of interest, which is f of C. So continuous at f of C such that we also have an algebraic expression here. So G at y minus G at f of C is equal to psi at y times y minus f of C. So the idea is that at any point where G prime exists, in this case at the point f of C, you can find one of these continuous functions, continuous at the point of interest, again, in this case f of C, such that G of a generic point minus G at the point of interest is equal to your function, psi of y, multiplied by the generic point minus the point of interest. Okay? So then the idea will be now, let's set, so having all this set, y equal to f of x and see what happens. Okay. So indeed, let's see what happens. Okay. So we're going to substitute, we're going to take this expression here and we're going to put f of x wherever we, we're going to take this expression here, the second to last line, and we're going to put f of x everywhere that we see a y. Okay? So that's going to give us g of f of x, minus g of f of c is equal to psi of f of x times, I guess, f of x minus f of c. Okay? And then we're going to, so this is us using the expression of Carathodory's theorem for the function g for the specific point f of c, and having replaced the generic point, or renamed, if you like, the generic point f of x. Okay, so really all we've done right here is use the differentiability of g at f of c along with Carathodory's theorem. We haven't yet used the differentiability of f and Carathodory's theorem for f yet, but we can, because in this expression we have this f of x minus f of c thing, and that is exactly the thing we can replace with an alternative expression using Carathodory's theorem. So this side then will be equal to psi of f of x times, this will be just phi of x times x minus c. I'm going to make a point of hiving off this thing here. Okay. Now what I'd like to point out is that we have something that looks like the algebraic expression you would expect to find for Carathodory's theorem applied to the composition of g and f. Why? Because here I have the composition of g with f in both places. So I have the composition of g and f at x minus the composition of g and f at c is equal to something times x minus c. And all that I need in order to apply Carathodory's theorem is for this thing, this blob, depending on x, whatever it is, to simply be continuous at c. As long as it's continuous at c, then whatever the value of this mess here is at c, that has to be the derivative of the composition, g composed with f. That's what Carathodory's theorem says. Okay, but then, in fact, this guy is continuous, right? Because Carathodory's theorem for g says that psi is continuous at f of c, and f is continuous at c. So in fact, this is just the composition of two continuous functions. So this bit right here, that's continuous. This we know from Carathodory's theorem for f. This is also continuous. And so what this is, ultimately, is just the product of two functions, each of which is continuous at c. And therefore, the product is continuous at c. Right? This thing here, this whole big mess, is just some function which is continuous at c. And so Carathodory's theorem says that as long as you know this function is continuous at c, then whatever its value is at C is the derivative of the composition. Okay? So now the question is, all right, that's great. We know that this thing evaluated at C is our derivative, but in the statement of our chain rule theorem, we had a pretty specific idea about what we wanted the derivative to look like. So we want to somehow unravel this thing evaluated at C to see that it is, in fact, equal to what we expect it to be equal to. So that's the last bit. All right, well, by Carathodory's theorem, phi at f of C is just G prime at f of C, right? And phi at C is equal to f prime at C. Those are both just restating an essential piece of the application of Carathodory's theorem to each of f and g. F is differentiable at C, so you get this. G is differentiable at f of C, so you get this. Right? And then you can see that if you take this product here and you evaluate it at C, what you're going to get is the product. So, right, if we take the product and evaluate it at C, then psi of f of C, phi of C is in fact exactly what we want it to be. G prime at f of C multiplied by f prime at C. And that is the chain rule, okay? And it's this Carathodory's theorem that makes it pop out as this product. Right? You first apply it to G, you get one function out here, and then you get another thing here to which you can once again apply Carathodory's theorem. And so in this almost trivial kind of rearrangement of the stuff, the material, in the definition of the derivative for a function differentiable at C, which is couched nevertheless as this theorem, this Carathodory's theorem, you can in fact get yourself a device that makes the proof of the chain rule extremely straightforward. Okay? All right. Well, that concludes the material that you will be responsible for on the final exam. That's the last thing there. Of course, as usual, if you have questions and so on and so forth, feel free to email. We can set up WebEx meetings. I've done a few. You know, for what it's worth, I know it's not my fault exactly, but I am sorry that things turned out this way. I know it is far from ideal. Believe me, I mean, the 4th grade has been kind of hard on me the second time around. I absolutely had no interest in relearning Brownsted-Lowry acids and bases either, so the 10th grade's been kind of miserable too. So I feel your pain. I had to go back to being a student in 2 different grades over the past few weeks. I've still got a few weeks left to go. And so, I mean, apparently we're all going to be in session in the fall. So, you know, I guess keep washing your hands. And all the best on the final. Again, if you have questions, I'm available. This is not goodbye, just farewell. And I will also be posting review notes and some review lectures in the coming week or so. All right. Take care out there. Be good.